Hello, my name is Luis Valencia, and this is my final frontier project. German physicist Werner Heisenberg determined that by observing the quanta of a particle, we affect the behavior of that particle. Even light can change the behavior of an object that is being observed. He began working on his theory of quantum mechanics in the 1920s, as the prevailing quantum theory worked for hydrogen atoms but not for larger atoms or molecules. This led him to the discovery of the Heisenberg uncertainty principle in 1927. The principle states that you cannot accurately measure a particle's momentum and position simultaneously, because while measuring these properties, the photons used to eliminate the particle would transfer some of their momentum onto it, which changes the velocity and therefore the momentum. Heisenberg used a thought experiment to confirm this principle. In this experiment, if he used a microscope to measure the position of a particle or an electron, it would give it a high energy kick. If you used a higher resolution microscope with higher energy light, it would give it an even larger kick. This shows how the more precisely you know its position, the less accurately your measurement of its momentum will be. Before this principle, it was thought that you could predict the position of a particle at any given time if you knew the position, momentum, or any of the forces acting on it at a certain time. This applies to multiple properties, but the most prevalent are position and momentum, meaning that the more precisely you try to measure its position, the more inaccurate the measurement of the momentum be, and vice versa. It is used to explain alpha decay, which is a kind of nuclear radiation. Alpha particles are emitted by heavy nuclei, such as uranium-238. A lot of energy is required to break the bonds that hold them in place. However, alpha particles inside the core of an atom have a highly well-defined velocity but less well-defined position. This means that there is a small but non-zero chance that that particle will find life outside of the nucleus at some time, even though it does not have enough energy. It helps us explain why atoms do not collapse into a ball of particles due to the attraction between the negatively charged electrons and positively charged protons. If the electron is too close to the nucleus, its position in space is accurately known. This means that there will be a large error when measuring its momentum. The electron would travel quickly enough to see the atom entirely. Newtonian physics claims that all variables of particles are measurable to an arbitrary uncertainty given good enough equipment, which opposes the uncertainty principle. Um, According to the uncertainty principle, when measuring the position of a particle using light and electron, for example, the photons of light will transfer a portion of the momentum to the electron, and it will move relative to this value. The principle does not apply to larger objects like a tennis ball or a car, because the transfer of momentum has less of an effect on it due to its larger mass. This is why we can accurately measure the velocity and position of a car using kinematics and all quantum behavior follows this principle, and it is important in determining spectral line widths, as the uncertainty and energy of a system corresponds to the line width seen in regions of the light spectrum explored in spectroscopy. This model assumes that particles are waves and vice versa. It also assumes that probability is all we ever know. The formula for calculating the uncertainty and momentum is delta x times delta p is greater than or equal to h over 4 pi, where delta x is the uncertainty position, delta p is the uncertainty momentum, and h is Planck's constant, which is 6.62 times 10 to the negative 34th power. Another pair of quanta that this applies to is energy times. This means that if you consider a small area of space-time for a precisely known amount of time, you cannot precisely know the amount of energy in that area. If this theory is correct, then particles must be popping in and out of existence in a specific area. The formula for the uncertainty of these two quanta is delta t times delta e, greater than or equal to h over 4 pi. Here's a helpful thought experiment that will help you understand the Heisenberg uncertainty principle. You are handed a tennis racket and are asked to go into a dark room. There are tennis balls being fired at you at random angles. Your goal is to strike a tennis ball with a racket. After striking a ball, its state has been changed. This is analogous to finding the position of an electron using photons. The photons used to find the electron have a small wavelength and in turn higher energy. and momentum. Once it hits the electron, it changes the state of being, and we cannot accurately know its position and its momentum at the same time. One important application of the Heisenberg uncertainty principle is quantum tunneling. Quantum tunneling is a phenomenon where a subatomic particle can be present on the side of a physical obstacle that it would normally not be able to go through. Although it cannot be explained by classical mechanics, it can be understood through Heisenberg's uncertainty principle. The uncertainty in the precise location of electromagnetic particles allows them to break the laws classical physics and propagate in space without going over the potential energy barrier. The odds of quantum tunneling events are 1 in 100 billion. Quantum tunneling is used to explain nuclear fusion in stars, even though the temperature of stars' core is not hot enough to overcome the repulsive forces. Quantum tunneling means that the sum of the billions of nuclei in a star can overcome this barrier and kickstart nuclear fusion. Another application is an STM tunneling microscope. Can we work around the uncertainty principle? A study conducted by Chinese physicists posits that if you line up a system of particles together before they enter an OTC-driven wormhole, they will exit from the other side almost exactly like lined up with one another. If all the particles are synchronized together like this, you don't have to worry about making individual measurements of each one. You can just measure the single momentum of one and the position of the other and apply that information to all particles in the system individually. Heisenberg recognized that if it were possible to measure both the momentum and position of simultaneously with greater accuracy, quantum mechanics would collapse, so he proposed that it must be impossible. Heisenberg's uncertainty principle redefined the laws of quantum mechanics. His principle applies to energy and time and position and momentum. It is used to explain quantum tunneling, which is an important aspect of the fusion of atoms and stars. It has been used to create microscopes that resolve individual atoms. That will do it for my presentation. Thanks for watching. Okay.